Hello, good morning, good afternoon, and good evening, everyone, depending on where you are. Welcome to today's the iCANX talk. I'm Xiaosheng Zhang from University of Electronics, Science and Technology of China. So today we have the very wonderful night, and this month actually we have the keynote speakers from over the world, and all these four speakers, I think they are the top tier scientists in the world actually. That is Professor Jay Lee, and for today's talk, and we also have the famous scientists and professors from Seoul and Delft and Tsinghua University. So today we have five the scientists to join tonight the iCANX talk, and so it's my great honor to introduce the group members one by one. So now we have Professor Lee from Shanghai Institute of Microsystem and Information Technology, and we also have the young models from the Wuhan University, that is Professor Guo Qiang, and we also have Professor Li Juanliang from Shanghai Institute of Microsystem and Information Technology. Actually, today the first time we will reform the iCANX. So besides we have the top tier scientists, and we also invited the young scholars to share the latest research activities. So and then we hope that you will enjoy today's the topics. So let's move forward to the first talk. So it's our great honor to have Professor Jay Lee from the Shanghai Institute of Microsystem and Information of the Systems, and that is from the Academy Science of China. So Professor Lee's current research interests include the design and fabrication and application of the micro and nano sensors, and he published many papers in journals with the high reputation, including Nanoletters, Small Carbon, and IEEE EDL, and all these the journals is top tier journals in the micro and nano fabrication and applications. And actually, Professor Lee also won the 5 the Chinese patents, and as well as the Japanese and some the US patents. And today, Professor Lee's topic is from MEMS to nano fabrication and the nano sensors. So without the further introduction, so let's welcome Professor Jay Lee for his wonderful talk. So Professor Lee, I will stop sharing, and you can share your slides and begin our talk.
Okay. Okay, could you see my slides now?
No, so maybe you should share the screen.
Yeah, I share the screen. Could you see it?
Sorry, maybe try again.
But okay, how about this time? No?
I see it. Anyone see
it? Oh, yeah, I think you should stop your sharing.
I think already.
Oh, I still seeing you share your screen.
Really? Okay. So
okay, Tay, you try again. So actually, Xiaosheng already
try it again. Okay.
Already share. I not the share screen actually.
Oh, but I think from screen, Xiaosheng Zhang is sharing the screen.
Really?
Okay. Could you stop it?
I think already. Okay, let me share my screen, and then okay. So now I share my screen, and then I stop sharing. Okay. So I try again. So can you try again now?
Okay, but I'm not sure what happened. I'm sharing my screen. Could you say?
No.
Tia, how many screen you have? So maybe you have few, yeah. So you try to change, the major one.
Okay. But I don't know what happened.
So maybe try again to see whether it works.
Could you see my screen now?
No,
No. What happened?
Yeah. so Tia, I suggest that you relog in, okay? You can drop
Okay.
on.
I will try it again. Okay.
Yeah.
Okay, so
See you soon.
yeah, and I didn't see the screen, so try logging again. So we have some minutes, I guess, to wait the Professor Lee to relog. So it's allowed me more time to give more introduction about Professor Lee. So Professor Lee actually is very top scientist. I guess it's not only in China as well as all over the world, specifically in the field of the microfabrication and application or some the device like advanced sensors. So today the topic from Professor Lee is, as I mentioned before, is from MEMS to nano fabrication and nano sensors. So actually I also have the abstract. So maybe before we enjoy the wonderful talk, I can give some to review a little bit the secret of the successful of the from Professor Lee. So as origin of the information in the real world, you know that the performance sensors are important not only to the human beings, but also to the smart robotics. So nanostructured materials has made it possible to form advanced sensors at ultra high performance. But however, the mass production at low cost is always the desirable, but it's very hard to achieve actually. So in Professor Lee, in the group led by Professor Lee, they already tried a lot of to make the devices to have the high performance, but they also keep the very low cost and make it the cost effective some high technology actually. So okay, so now warmly welcome Professor Lee come back and okay, now we have the screen. Okay, so
Okay.
we're ready to enjoy your wonderful talk. So the stage is for you.
Okay. Thank you very much, and sorry for the accident. It's my great pleasure to be here to give this talk. And it's not my first time to join iCANX, and I do enjoy the talk here. And today I would like to review my work in this decade, and from MEMS to nanofabrication and the nanosensors. I'm Tai Li from Shanghai Institute of Microsystem and Information Technology. And here is my outlines. At first, I will give a brief background introduction, and then it's the nanofabrication by MEMS technology. Following is the high performance silicon nanowire-based sensors. Finally is the summary. As we all know, sensors is more and more important in current and you can read from these slides. It's from one of my students' question. Some years ago, he just asked me a question because in current time, the microelectronics is very hot. And he said, how about sensors? So I give the answers as this slide show. Sensors is maybe more and more important in current real world because right now we can have some fashion world like Internet of Things, big data, and Industry 4.0 and cloud computing, and even ChatGPT. But it's all belong to virtual world. It's very important to have data in current time, and sensors may be the connection between real world and the virtual world. So we can call sensors as the source of data and the foundation of control. Here is an example in our current life. And here is the cell phone. You can find after the announce of the iPhone from 2007, all the cell phone has the same face, and it has it can see, it can hear, and it can talk, and it can feel. So it's just like a very close friend to us, and all these is benefit from the sensors. It has camera and microphone and a speaker and a touch screen. So right now we have so many sensors in our daily life. We make in a trillion sensor universe. It's from Fairchild company CEO. This could be the biggest business in the history of electronics. And we have the sensors with abundant and affordable. Yeah, its value is so high, it can make us touch the sensors every day, every time. And it's so convenient and efficient. And it should have a long life. Of course, it's mass manufacturing needed, and so we need the MEMS. We're lucky to have MEMS. As we all know, MEMS is a very mature technology in current day, and it's developed from the IC technology, and it can produce small size but high quality sensors with mass production and low cost. So in current time, we can have MEMS sensors in communication, automobile, medical service, and the aerospace, and even the industrial control. So that's what we have the sensors right now. But what's next? What's next for the sensors, and what's next for the future of sensors? In my laboratory, I may ask, maybe we can use nanowell. In fact, we have a lot of nanowells with various materials like silicon, zinc oxide, gold and copper, silicon carbide, silver, and a lot of nanowell. And silicon nanowell may be one of the best candidates for the sensors because it's materials for microelectronics, and it's compatible with the microelectronics technology. And it's very good to tune the electric property. And also, as a sensor, it's very important to modify the surface with a simple method. So right now, we can have some very high sensitive, high quality sensor with silicon nanowell. Here is a picture from the review paper published in Advanced Functional Materials. You can find that the silicon nanowell has been used to make different kinds of sensors, and it have the benefit of the mass production. So if we want to have a silicon nanowell sensor, we first of all, we should fabricate the silicon nanowell. Here is we have listed the method with the bottom up method, and in general it grows from the molecule precursors using nanoparticles as a catalyst, not only for VLS but also for SLS and LA. And also we can fabricate the silicon nanowire with top-down method. In general, it's to start from bulk materials and scale down the patterned area. And finally, we will have the silicon nanowire. It can use the metal-assisted chemical etching and nanolithography and anisotropic wet etching. Here is a comparison of these methods. And you can find the top-down method. It can be very nice to define the position of the sensor, the silicon nanowire, but it may cost high and the dimensional compatibility may be weak. But for the bottom up, although it may be easy to fabricate, but it's difficult to define its location. So for me, it's maybe a question. May we develop a method which can fabricate silicon nanowire sensor with high quality as well as a low cost? So in the last decade, we have fabricated the silicon nanowire by MEMS technology. Here you see some traditional MEMS process. It's include the oxidation, deposition, wet etching, dry etching, wet bonding. With all these traditional MEMS methods, it's possible for us to make the top-down method to make the silicon nanowire. Here is our answers. And we find 111 silicon wafer. Because we all know the 111 plane of silicon crystal is the self-stopping plane in wet etching. So if we have a 111 silicon wafer, we have a chance and we have wet etching, we will have a nanowire. And then after oxidation process, we can have a silicon nanowire on the wafer. So here is how we can control the process to reduce the size of the silicon nanowire. You can read the declaration of how we defined the width of the silicon wire. And we generally use three coefficients to define the size of the silicon wire. First is the depth of the etching windows, and the second is the etching time, and the third one is the offset angle. I can explain it in details. And the first part is we can define the depth of the etching windows. From this slide, you can see if we have the depth further, we can have the width smaller. So we can use resolution of lithography at 1 micron to define the size of the nanowire in 100 nanometer. So, and it can be controlled very precious. And the second part is to use the etching time. Of course, if you etching the silicon for longer time, you will have a smaller silicon nanowire. And the third part is the angle for the alignment. In general, it's random part, but if you use it very carefully, you can control the alignment angle very good. And if you can have the offset for 0.5 degree, you will have a size reduction at about 90 nanometer to 180 nanometer. So with all these three methods, we can fabricate the high quality silicon nanowell. You can find from this SEM picture, and the cross section of our silicon nanowell is triangle, and the surface of the silicon nanowell is very smooth. In other words, it's a very good high quality surface for the sensor. And we also can define all these configurations very carefully to have the horizontal and the longitudinal control of this silicon nanowell. You can find that just now we have the silicon nanowell on the top of the surface on the wafer, and then we can have the silicon nanowell at the bottom of the SOI wafer. And also we can do the process one more time to have the perpendicular aligned dual silicon nanowell. So with all this help of the 1.1 SOI, we can have the homogeneous silicon nanowell, and all these types of silicon nanowell is high quality, and it has very good stability, and it's possible to make high quality sensors. And here is how we make the high performance silicon nanowell based sensors. In fact, the principle of the silicon-based sensors is very simple. Because when the molecules, I mean the target molecules, is act with the probe, it will change the charge environment of the silicon nanowell and change the current in the silicon nanowell. It's so sensitive because it's in nano scale. So we can have the sensors with high sensitivity, and it's also very easy to integrate, and it's also level-free for bio detection or chemical detection. Here is our first example. We use it to detect DNA. We modify the surface with APTES, and then we use it to detect the target DNA, and we find that the detection limit can be as low as 1 femtomole. And it has a very good selectivity to distinguish H1N1 and H5N1. Even more, it's very sensitive to the SMP discrimination, and it will give the very typical response to the SMP target. So this is the possibility of our sensors to be. And also we can optimize the detect conditions of silicon nanowell sensors. we can change the working point of the sensor, and also we can use different buff concentration, and also we can optimize the probe concentration. With all this optimization, we finally improve the sensitivity of our silicon nanowell to 0.1 femtometer, and also we can improve it further. With the help of the RCA, we can even improve the signal to noise ratio to 20 for the 1 femtomole DNA. And it means it's possible to detect the 50 attomole DNA. So with all this possibility, we can have a very sensitive silicon nanowell sensor. Of course, because it's very sensitive, it will be sensitive to a lot of things. Maybe sensitive to the temperature, maybe sensitive to the pressure, and maybe sensitive to the wind flow, and a lot of things. So because it's made of silicon, we can make N-type nanowell as well as P-type nanowell. So we can integrate N-type and P-type nanowell together and use it to detect the same target. And because of the N-type and P-type, the response will be opposite, and we can use it to improve the signal noise and provide a very unique response to the sensing materials. And we have used our silicon nanowell to detect a lot of things. For example, microRNA and CA, this is a protein, and also a lot of things. So it can be used to detect a lot of bio molecules and also chemical molecules. But if we want to use it in our daily life, it's not enough. In current years, we have developed some method to calibrate our sensor. As I have said, the sensor is so sensitive. It was sensitive to a lot of things. So we just want to make it sensitive to what we want. And we find a way to calibrate with the optical response of silicon itself. So with this property, we have calibrated our silicon nanowell on the basis of the saturated photonic response. And then we can calibrate it very well. And also we have approach a new method with low salt concentration test environment. In fact, we have added the second buff concentration detection, and to use it to tell the difference between the initial and the final currents to show the signal to the real target. And then we can also calibrate it from the very complex environment. And here is the example of how we use it to detect MMP9. MMP9 is one of the marker for the dry eye disease, and its concentration should be detected in real tears. So the salt in tear will affect the result very strongly. With our developed methods, we can finally detect the precise concentration of the MMP9 in the tear, and this result is highly correlated with the ELISA result. And it's also shows that the good agreement with the clinic result. So it's possible to be used in the clinic measurement. And also we use this method to detect to have a self-content and integrate nanofluidic nano detection system. And we have all these analysis process include the liquid sample delivery, optical modulation, and constant temperature control, and signal amplification, and data acquisition, and result display. And finally, we can detect the AG85B continuously with high precision emitter. And it's possible for us right now to detect the exosome right now. And also we use our silicon nanowire to detect TNT, not only in gas condition, but also in liquid condition. In fact, it can detect the TNT even in 30% sulfuric acid. So we can find the TNT factory from the drum. So it will be very helpful to the place. And also we use this silicon combined with some biomaterials. This time we use the OBP protein, and it's from the mosquito. And we modified the OBP on the surface of the silicon nanowire and use it to detect the gas from human beings. And you can find with different OBP. It's from OBP1, OBP5, and OBP7, and OBP20. And it can detect different kind of have different response to the different gases. And with this spectrum, we can maybe use it to detect different, to say different person from one person to the others. So it's will be a very strong method to have electric nodes. And here we can have the summary. Okay, in the last decade, we have used the top-down MEMS fabrication method to fabricate the silicon nanowire. And also we use it to detect a different kind of biosensors, biomaterials, and the chemical gases. And we, in order to apply these silicon nanowire sensors in our daily life, we have developed some method, for example, optical calibration and the low concentration buff layer, concentration to make it possible to be used. And so in the future, I think we can have the silicon nanowire maybe in the POCT applications, and we can use it to detect different materials. Okay, here is the acknowledgement of this work. We have sponsors from the National Basic Research Program of China and the Creative Research of National Natural Science Foundation of China and the National Natural Science Foundation of China, and also from the EC Nanoman, from the Marie Curie actions. Thank you very much for your attention. Okay.
Okay. Thank you, Professor Lee. It's very, very wonderful talk. So maybe you can stop sharing, and then I could start to share my screen.
Okay.
Okay. Thank you. This let me share my screen here. So thank you so much for the wonderful talk. So even I have many questions, but I will keep them for the panelist discussion, the section. So, but I believe that just like me and the other the speakers and our audience, they have many questions for you actually. So as Professor said, actually we can do a lot for to make the sensitivity and the performance of the sensors better and better by developing some advanced the micro nano fabrication technology. So thank you so much. So now let's move forward to our the second the young scholar, that is Professor Guoqiang Wu from Wuhan University. So Professor Wu is currently a full professor in the Institute of Technological Science, Wuhan University. And Professor Wu's research group is focusing on the micro nano electromechanical systems, aka the MEMS and the NAMS, design and integration. He has served in the executive the technical program committee at IEEE MEMS in 2023 and 2024. That is the high repetition actually. He has published over the 17 articles and filed the over 15 patent applications, with 37 of them being granted in the United States and China, and some of them and already are successfully commercialized. So today, Professor Wu's topic is the MEMS resonators with the high temperature stability. So with that, Professor Guoqiang Wu, the stage is yours. So
Okay.
let me stop sharing, and then you can share the screen.
Okay. Hello, can you see me? See my screen?
Yes, no problem.
Okay.
So please.
Thanks very much for Xiaosheng's introduction, and thanks very much for Dr. Zhang and Dr. Lee's kind invitation. Good evening, good morning, and good afternoon, everyone. It's a great honor for me to present our work here in iCANX. I'm Guoqiang from ITS Wuhan University, and I graduated from CMAT CES in 2013. So Professor Li Tie is one of my mentor. So it is always a high pressure to deliver a talk in front of a mentor, especially deliver a talk after him. So I will do my best to give a good presentation here. Okay, the title of my talk is MEMS resonators with high temperature stability. Okay, firstly, let us to see what is a resonator and what's an oscillator. In fact, a resonator is a device which has mechanical resonance or resonant behavior. So we can use its mechanical resonance behavior as a frequency selective element. Last, we can use so compared with the classical electrical frequency selective elements such as LC tag, the mechanical resonators have much higher Q and hence have a better frequency selective capability, while the resonator's vibration will decay due to the inherent damping. In order to maintain the resonance, a sustain circuit is used to form an oscillator. The oscillator will produce periodic oscillation electric circuit signals. Currently, Coarse crystal oscillators and MEMS oscillators are the two main categories for mechanical oscillators. Coarse crystal oscillators were developed as early as in 1920s, so it has already have hundreds years history, and have since then it dominated the overall timing market. MEMS oscillators have experienced rapid growth and have demonstrated rivaling performance with the well-established coarse crystal oscillator. MEMS resonators have shown some great potentials to replace coarse crystal resonators due to their some good advantages such as compact size, fast reliability, and high temperature stability. Okay, according to yield development, the MEMS-based oscillator market is expected to reach 600 million by this year. So this data is not updated, so I should update it with a new one. And so we can see here it has a high annual growth rate. There are two main key performance merits for MEMS resonators. The first one is Q. For vacuum encapsulated MEMS resonators, there are two main energy loss mechanisms. The first one is the anchor loss. So the mechanical vibrations will leak from the supporting tailors to the substrate. It will cause energy loss, so we call it anchor loss. The other is the thermoelastic damping. So the damping is caused by the energy loss coupled from the mechanical domain to the thermal domain. The larger the energy loss, the lower the Q. The smaller the energy loss, the higher the Q, and the sharper the resonant peak. Thus, we can get a better frequency resolution. The other main performance merit is the temperature stability of a resonator. As we know, the resonator's frequency will shift with the operation temperatures. This is caused by two main factors. The first one is the material became soft with the temperature increases. And also the thermal expansion of the material will cause the dimension change, which also cause the frequency shift. The thermal stress also change the effective stiffness of the resonator, which can also cause frequency shift. In fact, high Q and low TCF are most desired for high performance MEMS resonators. There are some commonly used Q enhancement approaches. We can use some approaches to reduce the anchor loss, such as we can anchor the resonators at its node points. We can also use quarter wavelength Taylor. Also, we can use the impedance mismatch to reduce the energy loss from the resonator to the supporting tailors. Bragg reflectors can also reflect back the vibration energies. For thermoelastic damping, we can separate the thermal frequency with the mechanical frequency, so we can reduce the thermoelastic damping. We can also have some opening slots in the resonant beam to increase the thermal resistivity and reduce the thermoelastic damping. The other way we can operate the resonator in some low temperature where the thermal expansion of the silicon material is close to 0. So we can eliminate the thermal elastic damping. These are some common approaches. For passive temperature compositions, we can use composite structures because the silicon has a negative Young's modulus versus temperature, and the oxide has a positive one. So we can use some composite structures to make a composition. And also we can use geometric engineering to use the external thermal stress to compensate the modulus change caused by temperature. We can also use the degenerate doping or rotation tuning. In our work, we combine these approaches to make the resonator has a better TCF. In our work, we designed a Vance extension mode piezoelectric MEMS resonators. The resonators is designed based on a thin film piezoelectric on silicon platform. And we tune the resonators, we tune the resonator structure alignment. So for example, we can tune it aligned, the resonator is aligned from 22.5 degrees from 110 direction. Thus, we can have a better TCF performance. From the measurement results, we can see the resonators we fabricated have a unloaded Q around 10,000. The impedance is much lower than the quartz crystals. For the TCF curve, we have a better TCF performance than the classical 80-cut quartz crystals. However, as we can see here, although the TCF and impedance is much better than quartz crystals, but their Q factor is not high enough for high performance oscillators. So we have to increase the Q factor. In our work, we want to take both advantage of high Q from the capacitive resonators and also the low impedance from the piezoelectric resonators. So we design a mechanically coupled MEMS resonators. We use the piezo resonator to drive and sense the resonator, and the energy will trapped in the coupled square planes. So we can tune the Q of the coupled resonator by change the ratio of the coupled parts. From the measurement results, we can get a much higher Q for these piezoelectric resonators. Compared with the capacitive resonator, we have much lower impedance. Compared with the piezo resonator, we have much higher Q. So we have a trade-off between the high Q and the low impedance of these two resonators. And the Q versus the pressure is also characterized. The Q maintains very high below 100 pounds. So it has a high tolerance to the packaging qualities. From elevator deviation measurement, it has a very good performance. The stability is less than 1 ppb. We also use the mechanical coupling to do the TCF manipulations. We can use two modes. These two modes have different TCFs. So we can couple these two modes together to achieve a better TCF. As you can see here, when we change the volume ratio of these two parts, the TCFs will change accordingly. For these resonators, we use they are used as temperature compensated resonators, so we call it TCMO. But for high performance applications, we have to harmonize the resonator and predefined temperature. We usually maintain the resonator at its turnover point, so it will have less effect to the environmental temperature changes. So in this design, we use two modes. One mode is for frequency output, and the other mode is for temperature monitoring. So we can use the temperature monitoring resonator as an indicator to change the heating power and maintain the resonator at its turnover point. So the frequency output of the main resonator will have very high stability. In this design, we also use the phonolic crystals to reduce the anchor loss and reduce the thermal loss. We also use the locking amplifier to build two oscillation loop, and as you can see here, in the short-term stability testing, the frequency shift is less than 10 ppb within 1 hour. And we also have the real-time frequency measurement. In the real-time frequency measurement, we change the environmental temperature from -14 to 105 degrees. The heating voltage also changed accordingly, and the frequency stability, the frequency shift of the main resonator is less than 20 ppb within the entire industry temperature range. In order to reduce the mode coupling of these two modes, so we separate these two modes as two individual resonators. One resonator is for frequency output, and the other for temperature monitoring. The operation principles is quite similar with the previous work. We did the thermal design, and we have the thermal mode here. As you can see here, the two resonators have the same temperature, and the temperature difference between these two is very small. And we also have very good results here. We can achieve less than plus and minus 100 ppb frequency stability over the entire industry temperature range. Okay, the contents I delivered here, we also summarized in our review paper. Your citation and comments are warmly welcome. Welcome to visit our campus when you visit Wuhan, and thanks very much for the funding support from SFC. Thanks for your attentions, and my talk is over. Thanks.
Okay, so thank Guoqiang. It's very amazing talk, and your research, the research activities in your group is very excellent actually. So thank you so much, and maybe you can stop sharing, and then I can share my screen. Okay, so now let's move forward, and it's our great honor to have the third invited speaker, Professor. That is the professor from the SAM, actually is institute with Professor Li Tie, and so the professor. This is a professor, the Li Juanliang from Shanghai Institute of Microsystem and Information Technology. And so maybe Professor Liang, you can start. Maybe you can come to the stage. Let me, I didn't see. Okay, so thank you for open the camera. Okay, so now we have the Professor Liang. Professor Liang is associate professor in Shanghai Institute of Microsystem Information Technology and the Chinese Academy of Science. and the distinguished research, the backbone of the CES. And the master's the supervisor, and she received the PhD in Harbin Institute of Technology in 2016 and joined the Shanghai Institute of Microsystem Information Technology in the next year. And she has engaged research in the field of environmental the pollution monitoring, and she published a lot of very important the papers and with a high reputation in the journals. And she also is the principal the investigator leading the science and technology projects, the Class C of the Chinese Academy of Science, and as well as the NSFC. So Professor Liang, proud of you, and the stage is yours. So please, you can start to share the screen now.
Okay, let me share my screen.
Okay, so now we have. So
Okay,
please.
can you see my slides? Hello, everyone. Thank you for Professor Zhang's introduction, and thank you for Professor Alice Zhang to organize this talk. I will introduce our research work on real-time and online in situ monitoring sensor for water environment. And I'm Li Jianliang from Shanghai Institute of Microsystem and Information Technology. This is the outline of my presentation. And with the intensification of water pollution, such as the industrial pollution, the livestock waste, the living pollution, the water environment problems are increasingly worsening. And from the China Water Resources Bulletin in 2021, China's total water resources ranked 6 in the world. However, the per capita possession is ranked 88 out of 183 countries. So the current situation for water resources have the problem of shortage of total quantity and low per capita possession. In order to monitor the water quality, such as the sewage outlet, traditional methods include the laboratory testing or the portable instrument testing. However, these methods are time-consuming and inefficient. The online monitoring technique has the advantage of early detection of water quality abnormalities and could timely track the pollution sources. For the monitor sensors, they have also challenges such as the high specificity and the strong adaptability to extreme environments. And for the classification, I will introduce the classification and application fields of water quantity monitoring. And for the water monitoring, it includes the 5 water quality parameters, such as the pH, turbidity, conductivity, temperature, and dissolved oxygen, and other parameters such as nutrients, heavy metals, biological, toxic, and so on. And the sensors usually has the application on the surface water, industrial wastewater, and drinking water, and so on. However, they all include the 5 water quality parameters. And so our work mainly on this monitor sensors such as pH and turbidity. And I will introduce some of the monitoring sensors of our work. Considering the detection methods, the electrochemical sensor and the optical sensor are easier to achieve online monitoring. So we have developed 2 kinds of the sensors. For the electrochemical sensors, the parameters temperature, conductivity, and the pH. For the optical sensor, the parameters are dissolved oxygen and turbidity. This is the 5 water quantity parameters, parameter sensors. So first job, I will introduce our work on the pH sensor. The pH sensor is the electrochemical methods sensor. So it has electrode has 2 structure has 2 electrodes. The solid reference electrode is the reference electrode, and the sensing electrode is the the working electrode, and the electrode material is metal oxide. From this structure, we can see that the solid reference compared with the traditional electrode is the liquid. However, in our job, we developed the solid reference electrode, and this structure could reduce the cross contamination and improve measurement accuracy and service life. For the sensor productivation, we prepare the sensitive materials and develop the electrode sensor components and make the hardware and structure design. And finally, make the optimization and application validation. And this is the experimental results. We have the test from pH 1 to pH 12, and the sensor is very stable. Okay, here is a picture of exploited view. For the pH sensor, from the first generation to the new generation, we have developed the material structure and process optimization. And we have also determined the structure process and electrical components. For this sensor, it has more than 120 electronic components, and finally improve the stability and corrosion resistance and integrated transmitter. So this is the sensor technology. For our sensor, we also compare our instrument with well-known brand products, and this is the comparative analysis. We have improved the response time from 13 seconds to 5 seconds, and our electrode is the metal oxide electrode and has a solid reference electrode. Our second work is the turbidity sensor. This sensor has from this picture, we can see the structure has a scattering light measurement system and the dual light source dual beam system. This system could improve the accuracy and the repeatability in long-range measurements. And in front of the structure is the self-cleaning structure. This structure could reduce the maintenance frequency. Our sensor also has the turbidity sensor calibration certificate, and the indication error is less than 2%. Like the pH sensor, this is the exploited view, and we also optimize from the material and structure and finally determines the structure process. And this sensor has more than 280 electronic components. And this is the comparative analysis. We compare our sensor with the well-known brand and products such as Microsystem and and we have improved the temporal range and the response time to 10 seconds and the size. And with the cleaning brush, we have improved the accuracy and the measuring range. For this sensor, we also have the application cases. The sensor have also been verified in practical applications in hospitals and shopping malls in Shanghai under relatively harsh conditions, including the waste residue oil pollution on hospitals' sewage tank. We can see that after 6 months online monitoring, and this is the on-site maintenance. The sensor has the good performance, and the detection window is very clean, and the cleaning brush can work normally. Our third job is the conductivity sensor. This is the structure of this sensor. The electrode is a micro array electrode, and it has the 4 electrode structure, which could avoid cloned interference. And we also have the temperature compensating element, which could improve the accuracy. We compare with our sensor with the metal sensor, and the coefficient is very similar. Is 0.99998. And for the measurement range, from 0.5 to 13,000, which could cover the different water qualities from the newly distilled water 0.5 to the seawater 13,000. Also compared with the well-known brands, this is a competitive analysis, and we have improved the accuracy to 1 microsiemens centimeters. Our fourth job is the metal ion detection sensor. From the preparation of sensitive materials, we made the sensitive materials based on metal organic framework, and then we prepare the microcolumn array electrodes based on the silicon wafer substrate. The materials was filled on these electrodes by a vacuum pump, and then the multi-channel sensing model based on MEMS technology and microfluid technology. This is the picture. This is the channel layer and the PMMA testing tool and the electrode-based plate. In the circle, the red circle part is the microcolumn array electrodes. Based on our multi-channel ion detection model, we have made the online detection system, and it includes the circulation pole and the cleaning structure. Compared with the commercial sensors, the electrochemical characterization are similar. And this is the competitive analysis. This detection system could detect more than 10 ions, metal ions with the limitation of detection about 0.1 ppb. So based on our work of the sensors, we want to realize the online monitoring, and so we have established the monitoring system and the platform. And this is the water small floating ball water quality online monitoring system. It could realize the visualization and information of rivers and lakes water quality. In this part is the water quality monitoring sensors, and this is the positioning indicator module, and this is the solar panels. As the right picture is the water quality online monitoring system for water supply network. It could detect the drinking water, rural domestic water, and supply industries. And this is the monitoring system interface large screen. And in this part is the water quality monitoring sensors. It's the picture of the float ball. It could integrate multiple sensors, and this is the specifications. Considering the real-time and online monitoring, we have established the management system. It could realize the real-time monitoring and analysis of water quality and information. So we can effectively perceive short-term trends in water quality and assist the management departments in responding quickly to sudden situations such as water pollution. This system has been applied in more than certain regions, including environmental water bodies and sewage plants and chemical parks, which could provide scientific support for water environment protection. Okay, that's all my presentation. Thank you.
Okay, yes, Professor Liang, thank you so much. So now you can stop sharing the screen.
Okay.
Okay, so thank you so much for the wonderful talk. So exciting that we have these three very interesting and the research talk, and with remarkable the achievement actually. So now let's move forward to the panel discussion, and it's my great honor to invite Professor Haixia Zhang to join the panel discussion. So Professor Alice, if you are online, and maybe you can also open the camera. So now,
Yes, I'm here.
yes, this is the most exciting the section for the iCANX actually. It's a panel discussion. So I just very quickly and briefly introduce that. So today we have the very wonderful talk from Professor Li Jie and Professor Guoqiang Wu and Professor Li Juanliang. And we also invited the the Professor Haixia Zhang from Peking University to join us, serving as the panelist to join this the panel discussion section. So I believe that just like me, I think all of you are already enjoying this very excellent talk, and maybe you have so many questions. So this is also the first time. Okay, so we have Professor Alice is raised her hand. So maybe the stage is for you and to start the panel discussion. So Professor Alice.
Oh, okay. Yeah. Great. Thank you very much. Thanks everyone. Actually, this was the first time we try this new model. We want to have top scientist and the young scientist to go together for the related topic. So I'm so happy because today is from MEMS to nano fabrication, nano sensors. The title is my career. I was start my research was from MEMS. Now, yeah, we related to a lot of things to nanos, the sensors, fabrication, all these things. So as a more than 20 years old friend with Tae Lee. So yeah, actually I'm really proud of that, all the jobs you done and all the achievement, you have, in last 20 years is amazing. So for your talk, I mean, it's quite interesting because your talk was a major focus on nano sensors, and the two young scientists was for MEMS, the traditional MEMS, right? Yeah, resonators, oscillators, pH sensors, and all these, detectors. It's for MEMS. It's like 20 years, generations was growing, and then young generations growing. Yeah. So maybe I ask questions, from the Ted. So Ted Lee, Professor Lee, you see that, for silicon nanowires, right? It's a nano fabrication, right? Yeah. So the major kind of challenge for the nano sensors from nano fabrication is for the nanowires, how to, localize, right, exactly into the position. And even for the mass production, this is a big issue. I think you've done such a good job for the ultra-sensitive sensors arrays. How do you solve this problem? Please.
Yes. Nice to see you again, Alice. And it's my pleasure to join the iCANX again. And I'm glad to answer your question. I think it's very important to define the position of the silicon nanowire to make sensors. And so from the start, we would like to use the top-down method instead of the bottom-up method to fabricate the sensors, because we use the lithography method to define the position of this nanowire, and then we can define the electrode of these sensors. So we can find the sensors will be, and then we can do a lot of things to make the mass production. So based on this technology, we have made maybe thousands of devices on a 4-inch wafer, and then we use it to detect different kind of biomaterials and chemical vapor and other materials. And so I think with the help of the further methods such as the calibration we new developed calibration method and some measurement method way, and we finally will have a silicon nanowell to apply in the real life. Yeah, that's my answer. Thank you.
Okay, great. Yeah, that's also takes the advantage for the MEMS fabrication, I think.
Yeah,
the
sure,
technology.
absolutely.
Yeah. Okay, thank you very much. So Xiaosheng, can I add in one more questions?
Yeah, I think so. I think that we have the young scientists here, and the reason we provide this stage is to provide the young scientists to have the opportunity to challenge the top scientists like Professor Lee. So I guess the young scientists, they already have some questions, right? So maybe Professor Wu, and you have some questions for Professor Lee.
Okay. Thanks. Firstly, thanks very much for Professor Lithia's guidance and help during my PhD period. And I have one question. You give a fantastic talk regarding the biosensors based on the NAMs, right?
Yeah, sure.
If we from MEMS to NAMs for other sensors such as the physical sensors or I mean other optical sensors, is it any advantages, or do you have any comments or suggestions when we use NAMs for other sensors, especially for resonators?
Yeah. It's a nice question. I should say, because I would like to ask you this question. If your device goes to nanoscale, what will happen? Yeah.
Okay. Yeah. Because for some sensors, such as capacitive sensors, when we scale down the size, right? Some
Sure.
and some parameters will also scaled down, but some will remain. Remain as the MEMS one. So I'm not sure how should we design our sensors use the advantage of NAMs, especially, for example, my concern is for capacitive devices, we usually have some large capacitive phase rules. If we go to NAMs, how to avoid these? I mean, the signals may buried in the phase rules. So how should we avoid this when we design the NAMs sensors?
Okay. I think when you talk about the resonate, I think if it goes to nanoscale, it's two things should be mentioned. The first one may be the nano effect, because if the size of your silicon goes to nanoscale, it may has some different property for the silicon materials. For example, the Young's modulus will be different, so it will change the frequency of your device. And the second one is, as we all know, if we use the nano gap for this resonate, it may have a very large Q factor and improve the property of this device. And so in this case, it will benefit the property of your device, and maybe you can have bad application for your resonate. And I also have one question for your device. As we all know, you have tried to avoid the temperature dependence of your device, but it's also possible for us to make the resonate as a temperature sensor. So do you have any idea for these applications?
Okay. Thanks very much for your comments. So I will take your comments into I will take your suggestions into consideration when we design the MEMS resonators. Okay. For your questions, yes. We also have for resonators. For one thing, we will keep the frequency versus temperature as small as possible, the TCF as small as possible. On the other hand, we can also use the frequency dependency on temperature as a temperature sensor. So we can have some resonant temperature sensor, but I don't think it's a good topic for this kind of temperature sensors, because as we all know, if you want to have a good temperature resolution, you need the Q is high, right? You need a high Q. If you need a high Q, you need to vacuum encapsulate the sensors. If you have a vacuum encapsulation, so you have a very bad or very poor thermal coupling from the environment to the sensor, right? So I think it's, we can design a resonant temperature sensor, but in practical, I don't think it's a good concept for a product, because there are some trade-offs between the sensitivity and the resolution, because you need high Q, but you have a poor thermal coupling. So I don't think it will have a good performance for a good temperature sensor. That's my opinion. Maybe I'm not sure. Yeah.
Okay, maybe I can
Yeah.
comment on this. Yeah. So I think Ted gave you very tough questions. Yeah, this is true. Normally, for the sensors design, many people think of to be a multi-function sensors, right? Yeah, you can detect the several parameters in the same, kind of structure or devices, all these things. Yeah. But like Guoqiang says that for the application or real applications, a real product, the sensors must be a single mind, right? On one parameters, one time, there will be more, possible or feasible for the applications. I think, eventually we'll have many sensors, for research. I think this all can be touched, achieved. But for real application, especially for like a harsh environmental or this kind of, specific environmental requirement, one sensor, one parameter, that's the best way. Yeah, I think that's maybe the most suitable for mass production and stable, like this. So Ted, don't challenge the young, generation too much. Okay. Yeah, let's be kind. Yeah. Okay. Li Juan, maybe I can ask you a question. Yeah. So very nice, for the water or this kind of, detections is very important, and I don't think it is solved very well. Now a lot of places still need all these kind of sensors. I saw you give an example as a use like in the lake or in the ocean, you have a tank, right? Yeah.
Yes,
So
yes.
with the sensors detecting with the solar panels on the surface. So my question is for the, the energy part. So you use a sensor, so they must be long time, stable, in the lake or in some place. For the solar panel, is that, good enough for the, energy?
And
The
if
power? Yeah,
The solar
yeah,
panel in the lake,
yeah.
we usually use the solar panel.
I think is that enough? Yeah, the solar panel is for charging the battery, or you just use the solar panel?
And except the solar panel, we also use the Euro electric.
Okay. I see. How long it can stay? 6 months or,
6 months,
three?
more than 6 months.
Oh,
And this could for environment, we could adapt to the environment. In the lake, we usually use the solar panel, and in the lake in the Euro, we usually use the Euro electric.
I see. Yeah.
So-
Yeah. That. Xiaosheng, please.
Yeah. I mean, I have the similar question actually, because people talk about some system, and we always want to know how you can balance the power consumption and the power supply. Actually, since you use the solar cell, the panel, and if you consider the water wave, the situation is very complex actually. I guess it's not just can convert the light directly with the 100% the percent to transform to be the electricity. So have you calculated how much you have to supply in the power to make the whole system work? The system is continuously, and like we said, it's a self powered. Is it possible or not?
Thank you for question. As the environment is very complex, especially in the bridge. Under the bridge, the solar is not enough, so we use the Euro electric. However, in the ocean or the very large area, such as the ocean, we usually use the solar panel. However, the solar panel, how long we can use? More than 6 months. It usually depend on the parameters. More than 6 parameters or 8 parameters, we can use less than 6 months.
Okay, so maybe later we can talk more, and then to see whether maybe we can collaborate together to solve this problem. Because I in my lab and also have some research activities focusing on this the environment energy harvesting. So actually, I also have a question for Professor Lee. So this is so the precious opportunity for me. When I talk about we reform this kind of the iCANX platform, and we combined the top scientists to talk with the young scholar, the talk. But actually, I also belong to the young scientists. So
Yeah,
it's also also precious opportunity for me. So I have one question for Professor Lee. So since we have the young scholar today, and we also have the top scientists like you, so the topics, of course, 3 topics that are totally different. But my question is like this. Do you think that for the micro and the nano is a very exact some boundaries, like so MEMS micro fabrication technology is very powerful and even more powerful than the nano fabrication technology, like for sensors, or actually it's hard to say. That is very general questions, because people sometimes they say, okay, so maybe we don't need some nano materials, like you talk a lot about the nanowise, but maybe nanowise is not so, is very, very necessary to fabricate some very advanced sensors with the very high performance. I mean, some people, they do the research is for nano and with nano. Actually, the nano is not necessary. So it's very tough question.
Okay. Thank you. Thank you for Xiaosheng's question. And I think it's very easy to answer, because you don't need to fabricate in nanoscale. I mean, goes to nano field if the sensor is good enough. But if you want to improve the performance, you may need nanostructure. For example, for Professor Liang's sensor, if she can introduce the nanostructure on the surface of his electrode, she may have a larger signal to the current, but it's also have a trade-off, because this kind she should think about the stability of the nanostructure. So based on this, you should, if you want high sensitivity, you may need a nanostructure. If you want the high stability, you don't want to need a nanostructure. But if you have a production of the nanostructure, you may have stability also. So it's depend on the applications, and you don't need to define I need to do it in nanoscale or not. It's all based on the application. That's my answer.
Okay, thank you so much. So so Professor Liang, maybe your question, yes, please.
Okay, thank you for Professor Lee's excellent jobs. I have one question. For the sensors, especially used in the practical application, I want to know how to solve the impact of the temperature and the humidity on sensors. That's my question.
It's a very good question. If you want it makes the sense in the real application, you have to solve this problem, I should say. And in general, there are several methods. For example, for the gas sensor, infrared gas sensor, it's also in my group. We use a additional filter to avoid the influence of the other gases, to make it selective to only one gas. And also for the temperature influence, we used a table to check the response, and then we can find the real concentration of the sensor. Yeah, so also we can have a reference for the sensor, and then you can prevent the influence of the environment totally, and find the signal exactly. And so I think it has a lot of method being developed to avoid the temperature dependence. And you should just try and find what the factors will affect you, will influence your senses, and find the best way to solve it. That's it.
Okay.
Okay, so yeah, thank the Professor Lee. It's very exciting, the discussion section. It's just like the topic delivered by Professor Lee, from MEMS to nano fabrication and nano sensors. So do nano when you need nano. Okay,
yeah,
so
sure.
Yeah. So okay, so the super exciting discussions. I think a lot of the audience and the scientists, they enjoy this the brainstorming here, and the casting up the new ideas, and so proud of that. But actually, the time is almost up, and today we have the very great talks from the three professors. And I like this the new form actually. I believe that we will have very successful in the future. You mean you just reform and you have new ideas and bring some top scientists and young scholars together. So and we have a very wonderful discussion, and also with Alice. So maybe I just move forward to the next stage, step. And then we have some certificate to Professor Lee Tie, and this is for you. And thank you for your great contribution to the iCANX the talks. And we also have the certificate for the Professor Guoqiang Wu from Wuhan University. Thank you so much to join this. This is the first time we invited two the young scientists you stay at the same stage with the top scientists. And then we have the certificate for the Professor Li Junliang, and thank you so much for your great contribution to iCANX. And as said by Alice, and we always need to invite some, the female scientists to join us, and then to make the world become better and better and greater and greater. So thank you so much. So then we have the very exciting night. And then finally, I just announced that we will have the iCANX talks volume 119, and will be delivered. The talk is be delivered by the Dae Yong Kim from Seoul National University, one of the top tier the research institute in the world. And the topic is about the nanomaterials based soft bioelectronics and its applications to the cardiovascular the disease. And we also have the three the panelists, the members, that is the mononator, the Misu Kim, and we have the panelists, the Xin Shen and the Yu Qingzhen from the Tsinghua University and Peking University, respectively. So thank you so much for enjoying. I hope that you enjoyed the exciting night, just like me. And see you next Friday. Bye-bye.